Okay, so today we're going to be talking about diagonalization. We're going to be talking about diagonalization. Okay, so remember the thing that we did last time was show that if you have an n by n matrix with some distinct eigenvalues, with corresponding eigenvectors v1 through vk, then the vi must be linearly independent. Okay. So you have a bunch of eigenvectors corresponding to distinct eigenvalues. Then those guys are linearly independent. Yeah.
By distinct, do you mean there's no repetition?
That's right.
Okay.
That's right. That's right. So you've got all different. You've got a bunch of different eigenvalues. Okay. It may well be. Notice that this k is not n, right? So we're not saying that you have n different eigenvalues. We're just saying take some. This thing has a bunch of eigenvalues. Take the distinct ones. Then, if you have eigenvectors corresponding to those distinct ones, then they form a linearly independent set. Okay. Now, that of course that implies, right, if A has, right, n distinct eigenvalues, then there exists an orthonormal basis. There exists a basis of eigenvectors. Right? A basis of Rn consisting entirely of eigenvectors. Right? Because then you'd have, you have n eigenvalues. You take an eigenvector corresponding to each one, and then that gives you n linearly independent vectors, and so that forms a basis. Okay. So that'd be nice if you had n distinct eigenvalues. Okay. And we'll see why that's actually something desirable. Okay. So definition. Again, you have a square matrix. If there exists an invertible x in Rn cross n, such that x inverse Ax is diagonal, then we say A is diagonable or diagonalizable. Okay. And we also say that A is diagonalized by x. So nothing fancy yet, right? We're just introducing a term, right? If you have a matrix and you can conjugate it by some other matrix and get a diagonal matrix, then you call this guy diagonalizable. Okay, right. So in other words, if you're similar to a diagonal matrix, you're diagonalizable. Okay, so nothing is perfect. Okay. Let's see. I think I have enough space here. So theorem A is diagonalizable if and only if A has n linearly independent eigenvectors. So again, A is a n by n matrix. Okay. In other words, right, your matrix is diagonalizable if and only if the you have a basis of eigenvectors. Okay. So that tells us that our corollary, what our corollary says is that if you have n distinct eigenvalues, then you're diagonalizable. So, right, if you have n distinct eigenvalues, then you have a basis of eigenvectors, and what we're seeing over there is that having a basis of eigenvectors is equivalent to being diagonalizable. Is that right? Okay. Okay. So so let's do the proof. Suppose there exists a basis B1 to Bn of eigenvectors. Okay. Let X be the matrix that you get by using those guys as columns. Now, let's consider AX. What's AX? Well, of course, it's going to be AX. Right? What happens when you multiply this thing by A? Well, when you do matrix multiplication, right, you're going to have A. Does anyone know what's going to happen? No, it's okay. Right, you're going to get AB1, AB2. Right? It happens column-wise. Okay. But each of these guys are eigenvectors, right? So that's just the same thing as and I should say corresponding to lambda 1 through lambda n, respectively. Okay. But you can rewrite this guy as B1 through Bn times the diagonal matrix consisting of the eigenvalues down the diagonal. Right? If you multiply these things together, then you're gonna get this. Right? And so what does that say? That let's write that as xd, right? This thing is x. Let's call this thing d. And so we get ax equals xd, right? ax equals x times the diagonal matrix, right? Which gives us that x inverse ax is diagonal. Right? So just a matter of calculation. So if there exists a basis of eigenvectors, then you get a if there exists a basis of eigenvectors, you just conjugate. You make a matrix of those eigenvectors, and you conjugate the matrix, and you end up with a diagonal matrix. And in particular, you end up with a diagonal matrix with the corresponding eigenvalues down the diagonal. Okay. Any questions about that? Any questions? No. Okay. Okay. So now we need to go the opposite direction, right? The opposite direction is equally straightforward. Suppose you are a diagonalizable matrix, right? Suppose your matrix is diagonalizable, right? Well, that tells you that AX equals XD, right? That's to say that A right? That tells you that this is true, right? AX equals XD. Right? The end, right? The end, because this thing on the right is going to turn into, of course, d11x1, dnn(x2), right? And then your knowledge of matrix multiplication, right? On the left-hand side, you know that this is ax1 through axn, right? So that tells you that ax1 is d11x1, ax2 is d22x2, etc., etc. All of these guys are then eigenvectors with these guys being the eigenvalues, right? So xi is then in dii. And so you have a basis, right? Right. So you already knew that these guys were a basis. Why did you know these guys were a basis? The xi's you knew from the beginning were a basis because x is invertible, right? X is invertible. So you know that these columns are linearly independent, right? So you've got n independent vectors, they form a basis. The thing that you needed was just one more fact, that they were also eigenvectors, right? So we have a basis of eigenvectors. Okay, so that's the end of that theorem, right? That diagonalizability is equivalent to having n linearly independent eigenvectors. Okay, so for example, if I give you a matrix and I say diagonalize it, what do you need to do? What do you need to do? All you need to do is find a basis of linearly independent eigenvectors, right? So you need to find a bunch of eigenvectors. Okay. Take 1 minute or so. Take a minute and sort of sketch out what you need to do and maybe get started on some of it. Okay, so what do you need to do? What's the first thing we should do? Finding the eigenvalues, right? So let's do the characteristic polynomial, right? So you say, okay, let's take the determinant of 5 minus lambda, 6, -2, -2 minus lambda, right? 5 minus lambda, -2 minus lambda, plus 12. And you get lambda squared plus 2 minus 5, so that's minus 3. Minus 3 lambda minus 10 plus 12. Lambda squared minus 3 lambda plus 2, so lambda minus 1, lambda minus 2. Right, so 1 and 2 are the eigenvalues, right? And so at this point, you already know what the matrix is going to look like, right? When we multiply it by the right thing, it's going to be 1, 1, 2, or 2, 1, depending on your choice. So then you need to find eigenvectors, right? So let's look at what E1 is, right? E1 is the null space of 5 minus 1, the null space of this, right? So you get right. So 1, 1 and 3/2. Right. In other words, x1 is going to be -3/2 of f2. So this is E1, right? And E2, right? It's going to be the null space. We need to look at law minus 2, so 3, 6, -2, -4, right? That's equivalent to 1, 2, right? And so the null space looks like -2, the span of -2, 1. Right. Okay. So then, right. So then you just conjugate. You say, okay, I know that 5, 6, -2, -2, and let's take them in whatever the order that I have here. -3/2, 1, -2, 1. Right. -3/2, -2, 1, 1. Inverse is going to be 1, 0, 0, 2. Right? By what we just said, that if you conjugate your matrix with a matrix consisting of whose columns are an eigenvector basis, and you're going to end up with the corresponding eigenvalues down the diagonal. Notice, of course, if I'd used the columns in the opposite direction, then I would have gotten a 2 here and 1 here, right? Of course. Any questions? Any questions? Okay, so so you can diagonalize your matrices. Okay. Bunch of definitions. First, if A does not have n linearly independent eigenvectors, why do I say this? If A is not diagonalizable, hear this term very often. Rather, I hear not diagonalizable. Okay, so
Very harsh way of putting it.
defective.
Yeah.
That's just the term. I mean, we also use the term degenerate for other things. Oh, that's the degenerate example. So, yeah. Yeah, I'm afraid that's just the language. Although I don't hear people say this. Oh, the matrix is defective. Yeah, so I'm going to say that I think this is non-standard. You know, anyway, non-diagonalizable. Okay. Definition number 2. Say lambda naught is a root of the characteristic polynomial. Okay. We call the degree of the root, right? The degree of lambda naught as a root, the algebraic multiplicity. Of lambda naught. So, right, if the so for example, if I have a matrix A which is 2, 0, 0, 0, 4, 0, 1, 0, 2, say, then the characteristic polynomial looks like lambda minus 2 squared, lambda minus 4, right? And so 2 and 4 are your eigenvalues, and 2 has an algebraic multiplicity of 2, 4 has an algebraic multiplicity of 1, right? 2 is a double root, so we say it has algebraic multiplicity of 2. 4 is a single root, has an algebraic multiplicity of 1. Just terminology. Okay. 3. Again, let lambda not be a root of the characteristic polynomial. We call the dimension of the eigenspace the geometric multiplicity of lambda naught. Okay, going back to our example again, right? Let's look at E sub 2, right? E sub 2 is the null space of 0, 0, 0, 0, 2, 0, 1, 0, 0. Right? Which says that x1 can be anything, right? x2 is 0 and x1 is 0, x1 is 0, x2 is 0, and x3 can be anything. Right? So this is the span of that. Right? Because our conditions are 2, x2 is 0, and 1, x1 is 0. Right? And x3 can be whatever it feels like. Okay. And so the geometric multiplicity of the eigenvalue 2 is 1. The algebraic multiplicity was 2, but the geometric multiplicity is 1. Any questions? Any questions about those two things? So those are somewhat different things. They are different things. They're related. There's a relation between them, but they are not the same thing. What do you think the relation is between these two things? Is there some relation between the algebraic multiplicity and the geometric multiplicity? Are they completely unrelated? Mia?
Is the algebraic multiplicity always greater than or equal to the geometric?
Yes, yes. Why do you think so?
I took differential equations last semester.
I see. Okay, okay. So think about it for a minute. Think about it for a couple minutes and see if you can give me some reason why the geometric multiplicity is always going to be smaller than or equal to the algebraic multiplicity. And the algebraic multiplicity is always going to be bigger than the geometric multiplicity.
If the geometric multiplicity is greater, would it not be linearly independent? Or would there be like some repetition? So it's not possible.
Well, so are you saying that you can't have more eigenvectors? You're sort of saying that you can't have more eigenvectors than.
What, like one eigenvalue can't have more than 2 different eigenvectors?
That's not true, right? Because the eigenspace actually has an infinite number of guys, right? Elena.
Like the multiplicity of the eigenvalues, like the cap on the number of like eigenvectors associated with it.
Yeah, that's sort of saying the same thing, right? That the algebraic multiplicity sort of bounds bounds how many dimensions the eigenspace can have, right? So this is what we're guessing, right? That the algebraic multiplicity is some sort of bound, some sort of control on the dimension of the eigenspace, right? Right. And so, so if this is true, and this is true, thus one has a basis of eigenvectors only if and only if the geometric multiplicity equals the algebraic multiplicity for all eigen values. Right? That's the only way that's going to happen. Right? Because the sum of the algebraic multiplicities is n. Right? The only way you're going to get to n is if all the geometric multiplicities are as big as possible. Right? That's the only way they can all. These things sum to something less than or equal to n. Right? And it's only going to be equal to n if they're full. So we know, for example, that this matrix here, this matrix is not diagonalizable. Right? Because we just saw that for one eigenvalue, the geometric multiplicity is not equal to the algebraic. Okay, so we know So we know that this matrix, you can't diagonalize it. Okay, let me sort of give a sketch of why this happens. Let's say that the geometric multiplicity is of some eigenvalue is d. So let d be a root of the characteristic polynomial, and say that the geometric multiplicity is d. In that case, there exists d linearly independent eigenvectors v1 through vd in E sub lambda naught. Right? Like geometric multiplicity is d. In other words, the dimension of that eigenspace is d. In other words, you have a basis of d vectors. Okay. You can use those guys to half diagonalize A. So take A and use V1 through VD, and then just fill in with garbage afterwards. Okay. But fill in with a basis. Okay. So fill this up to some basis. But these are not. You don't know that these guys are eigenvectors. Okay. Okay. So complete a basis of Rn using, right? So create a basis V1, VD, VD plus 1, Vn. Right? Using those guys as the first elements of your basis. Okay. Then conjugate using that matrix. And what you get is going to be lambda naught d times, and then some stuff down here. Okay. You know, just by your understanding of matrix multiplication, you can see that this is going to happen. Okay. But that tells you then that the determinant of A minus lambda I is going to be the same as the determinant of this thing minus lambda I, which is lambda naught minus lambda to the d times the determinant of B minus lambda I. Okay, and so what does that tell you? That tells you that the algebraic multiplicity of lambda naught is at least B, which was the geometric multiplicity of lambda naught. Right? Because at least you know that, there are d powers of this. This is a root of d multiplicity, and maybe higher. Who knows? Maybe in this thing you also get more powers of lambda naught minus lambda. Okay. But at least the power is d. Okay. So the algebraic multiplicity is going to be greater than or equal to d. Any questions about this? Any questions? Okay. Okay. Let's see. Well, okay. Why don't I make you guys work a little bit? So some simple questions. Yeah. I think you have seen the term nilpotent matrix in your homework. Is that right? Have you seen the term nilpotent matrix? No, you haven't. Oh, okay. Okay, in that case, this will be harder than I thought. Okay. Okay, so but we can still do it. So in that case, I'll do it in pieces. Okay. So a nilpotent matrix, a nilpotent matrix for A, we say A is a nilpotent matrix if A to some power is the zero matrix. Okay. So here's the two-part problem. First, show that that if A is nilpotent, then all of its eigenvalues must be zero. Yeah, all of its eigenvalues are zero. Okay, and part two, if A is a non-zero matrix and is nilpotent, then it's defective. Okay. I don't know how you feel about this, Teresa. Not only calling it nilpotent, but
defective.
yeah, it's defective. Okay. Okay. Let's for now. Let's just assume the first one. Okay. Let's assume this one. And see if you can get the second one. So suppose you know all its eigenvalues are going to be zero. Why then is it going to be defective? Why then is it not diagonalizable? I guess feel free to work on either part. I guess the first part is actually probably more instructive. Anybody have some idea on either one, or talk to somebody next to you for a minute? Learning to talk about mathematics is a really useful skill. I think. I never spoke to anybody when I was an undergraduate. Throughout my entire undergraduate education, I don't think I talked with anybody about problems. And then I went to graduate school, and then continued not to talk to anybody. But I see that the people who actually learned how to talk math with other people, they get ideas, they work with others. They're far more productive. It's a useful skill. Talk to each other.
So I thought it was in the A is one.
Let's determine it.
Actually, I should say that I actually did talk to a couple of people. I remember once in my freshman year, I tried to talk to somebody on a math problem, and then, but that wasn't very successful. And then there was this other guy who would often talk math to us. He was sort of an odd guy. He always talked in a monotone, and so he'd come up, he'd be brushing your teeth in the morning, and he'd shuffle over and say, "Do you know what a super topology is?" What? A super topology is, and then he'd start defining what a super topology is. A super topology is something that, it's like, go away. You're brushing my teeth. Yeah, so I talked with him. I once tried to work with him on homework, but it wasn't productive. Yeah. So anybody have any idea? We have 1 minute. So here's one way you might do the second. So suppose it's not defective. Suppose A is not defective. Right? In that case, you can conjugate it and get a diagonal matrix. Right? What's wrong with that?
All the eigenvalues 0?
Yeah, all the eigenvalues would be 0, so this would be the 0 matrix, and then A would be the 0 matrix, right? But you said we assumed A was not the 0 matrix. It's a contradiction. Okay. Did anyone make any headway on the first one? If A is nilpotent, in other words, some power of K is the 0 matrix, then all the eigenvalues must be 0. Okay, maybe we'll start off with that one next time. Okay.